Imagine you're tasked with building $100 million skyscraper.
Oh, wow. Okay.
Yeah, right? And you and your team have spent, I don't know, months calculating the steel framing to the absolute millimeter.
Mm-hmm.
You know the exact load capacity of every single I-beam. You look up the stiffness of the concrete in a manual, and it gives you this clean, reliable, constant number.
Right.
But then you have to look down at the dirt you're actually building on.
Yeah, that's where it gets tricky.
Exactly, because that dirt might have a physical memory of a glacier that sat on it, 10,000 years ago.
Yes.
And if you don't account for that prehistoric memory, your flawless $100 million building is just going to sink straight into the earth.
It really is staggering, the contrast between manufactured materials and geological materials.
Yeah.
Because assuming that soil has a single constant stiffness, the way steel or concrete does,
Right.
it's perhaps one of the most dangerous illusions in geotechnical engineering.
Mm.
Yeah, we're dealing with a dynamic physical landscape that is quite literally a moving target.
And that moving target is our entire mission for this deep dive, because we're looking at this massive stack of geotechnical engineering manuals, laboratory testing protocols, and the original soil mechanics papers that outline the Janbu stress-dependent Tangent-Modulus.
Which is a mouthful.
It is a massive mouthful. It sounds like this formidable wall of academic jargon, but the core problem it solves is actually incredibly relatable.
Oh, absolutely.
Because to picture why a constant modulus fails in dirt, I was actually thinking about packing a suitcase for a really long trip.
Oh, a suitcase.
Yeah.
That's a brilliant way to visualize soil mechanics.
Right. Because
The mechanics of compression are remarkably similar there.
yeah, so, okay, you throw your first few T-shirts into an empty suitcase.
Mm.
They compress super easily. The stiffness of that little pile of clothes is very low.
Right.
But as the suitcase fills up, the pressure builds.
Yeah.
So pushing down to squeeze in just one more heavy wool sweater takes this massive amount of physical force.
Exactly.
So the squishiness of the clothes isn't a constant. It changes based on the pressure that's already trapped inside the luggage.
And dirt does the exact same thing under a building.
Really?
Yeah. The compressibility of soil is constantly changing based on its current effective stress, its density, its microscopic structure, and its loading history.
Okay.
So a single constant modulus completely hides the true stress path of the soil.
Right.
And that changing stiffness, that's the exact problem the Janbu model was built to solve.
Oh, I see.
Instead of pretending the ground has this fixed squishiness from the surface all the way down to bedrock, Janbu replaces that fixed assumption with an instantaneous constrained tangent modulus.
Okay.
In the literature, you'll see it called M sub t.
Okay, I want to make sure I'm visualizing this correctly. So this M sub t isn't just a number you pull from a chart.
No, not at all.
It's like a formula that actively tracks how the stiffness of the dirt increases as the pressure from the new building increases.
Yes, it is continuously evaluated along the actual vertical effective stress path.
Wow. Okay.
And the Janbu equation handles this shifting target elegantly using just a few key variables.
Okay, lay it on me.
So it states that the tangent modulus is equal to a modulus number, which is m,
Right.
multiplied by a reference stress.
Okay.
Then you multiply that whole thing by the ratio of the current effective stress to the reference stress, and all of that is raised to the power of 1 minus j.
Okay, I'm going to be honest, my eyes usually glaze over when we hit the pure algebra in these papers.
That's fair.
But let's break down the physical meaning here, because I think I've got it.
Sure.
The reference stress, or sigma r, that just seems to be a baseline, right?
Exactly. The manuals conventionally set it to 100 kilopascals just to keep the mathematical units clean.
Gotcha. And the effective stress is just the actual pressure the soil is feeling at that specific depth.
Yeah.
So the real heavy lifters in this formula are those two dimensionless parameters, right? The exponent j and the multiplier m.
Oh, completely. Those two parameters are the entire engine of the Janbu framework.
Okay.
Let's look at the stress exponent first, so Jj.
Right.
This parameter dictates the shape of the stress dependence. It's basically the dial that controls how the stiffness changes as you apply more pressure.
So it defines the curve of our suitcase analogy.
Yes, exactly.
And if I'm reading the sources right, different types of dirt have totally different J dials.
They do. We generally rely on 3 benchmark cases for that exponent.
Okay.
So for normally consolidated clay, picture a very soft, fine-grained soil.
Like mud.
Yeah, basically mud. The J value is 0.
Okay, 0.
And when J is 0, the math dictates that the modulus increases linearly with stress.
Okay, so that covers the soft clay. But what if our site is sitting on a beach or, I don't know, a massive deposit of sand?
So for sands and silts, engineers typically use a J value of 0.5. This creates an intermediate stress dependence. The soil's stiffness is proportional to the square root of the effective stress.
Got it.
And finally, you have situations where J equals 1.
Wait, if J is 1, then 1 minus 1 is 0.
Exactly. So in the equation, raising that stress ratio to the power of 0 means the stress term effectively vanishes,
Oh, wow.
and the modulus becomes a flat constant.
Huh.
We only see J equal to 1 for linear stress-strain responses,
Okay.
which happens in very, very dense geological material or during what we call recompression.
Recompression. Okay. Well, I do want to throw out a quick warning I caught in the literature about J.
Oh, the notation issues.
Yes. Because if anyone is looking up supplementary textbooks to follow along, you might actually see this stress exponent written as A or N instead of J.
Right, the letters change depending on the author.
Yeah, but they're only mathematically equivalent if they're sitting in that exact same spot in the exponent.
That's a very good point to make.
And our sources emphasize this. They say never to introduce the symbol beta into your project unless it is explicitly defined,
Please don't.
because it means entirely different things in different engineering codes.
It does. Engineering notation is, well, it's notorious for creating confusion across different eras of research.
I can imagine.
Identifying the physical behavior behind the letter is really what matters.
Okay, so let's shift to that second parameter then, m, the modulus number.
Right.
If J shapes the curve, m acts as the multiplier. It scales the overall stiffness.
Mm-hmm.
So a higher m means a higher modulus, which translates to lower compressibility.
Exactly.
The dirt is fundamentally less squishy. So if I have a massive m value, my building is going to settle a lot less.
Yes. A higher modulus number dramatically reduces your calculated strain increment.
Okay.
If you double the m value for a specific soil layer under the same load, you are essentially cutting the expected settlement of that layer in half.
Well, here's where I have to push back, though.
Uh-
If m is just a scale of how squishy the soil is, why can't I just go to an appendix in a geotechnical textbook, look up the m value for, let's say, a medium-dense sand,
Oh boy.
and just copy-paste that single number across my whole site model? I mean, it would save me thousands of dollars in lab testing.
Yeah, copy-pasting a textbook value across a whole site is a fantastic way to design a failing foundation.
Oh, that bad.
That bad. The modulus number m is emphatically not an immutable soil constant, like the atomic weight of carbon.
Okay.
You cannot just look it up. The fitted value of m changes radically based on the soil's in situ density, its microscopic fabric, any natural cementation between the particles,
Wow, okay.
and how badly the sample was disturbed when the drill rig actually pulled it out of the ground.
So it's super sensitive.
Very. And beyond all those physical factors, the value of m changes based on which loading branch the soil is currently experiencing.
The loading branch. Okay, this brings us back to the glacier. And what I think is honestly the most mind-bending part of this entire topic, which is the physical mechanics of soil memory.
Stress history is the foundational reality of the Janbu calculation.
Right.
A soil layer inherently remembers the absolute maximum stress it has ever felt in its entire geological history.
That is wild.
Engineers call this critical threshold the yield stress, or sigma prime p.
But how does dirt actually remember weight? I mean, it doesn't have a brain. What is physically happening underground when that glacier sits on it for a few centuries?
It comes down to the microscopic architecture of the soil grains themselves.
Okay.
When a massive weight like a glacier presses down on a soil deposit, it physically forces the individual particles to rearrange.
Oh, I see.
Yeah, they slide past each other, they crush at their contact points,
Yeah.
and they lock into a denser, tighter fabric.
Right.
And here's the thing, even after the glacier melts and the weight is completely gone, those particles remain locked in that dense configuration.
So the soil fabric has been permanently altered by that historic pressure. So the yield stress is just the physical limit of that microscopic lock-in.
Precisely.
And because of the structural memory, the Janbu settlement calculation forces engineers to break their math into 3 very distinct scenarios,
Yes.
depending on where the weight of our new building sits relative to that historic yield stress.
Right. So the first scenario is recompression.
Okay.
This happens when the starting stress in the ground plus the final load of your new structure both remain below the soil's historic yield stress.
Got it.
You are merely reloading the soil to a weight it has already comfortably held in the past.
So to bring the suitcase back, recompression is like pressing down on a suitcase that is already packed tightly.
Yeah.
You're applying pressure, but you aren't really forcing the clothes to adopt a totally new shape. It's
right.
relatively stiff. It just doesn't give much.
Exactly. In that state, the soil behavior is quite rigid.
Okay.
Engineers use the unloading or reloading branch of the stress curve, representing it with a specific recompression modulus number, MC bar.
M sub. Okay.
And in this branch, we often treat the soil as having an approximately constant constrained modulus.
Because it's acting stiff.
Right. But the math completely changes in the second scenario, which is virgin compression.
Virgin compression. Okay, that sounds like we are breaking new ground.
Literally.
Great. So this is when the starting stress of the site is already at or beyond the historic yield stress.
Mm-hmm.
Every single pound of steel and concrete we add is a weight this soil deposit has never experienced before.
And that's when the microscopic locked-in structure begins to actively break down and yield.
Oh, wow.
The particles are sourced into entirely new configurations.
So it gets squishy again.
Much more compressible. This is where you deploy the virgin parameters, so the fitted M and J values, over the applicable stress range.
Okay. And then there's the third scenario, which seems like the trapdoor where the most catastrophic engineering mistakes happen.
Oh, yes.
Crossing yield. This is when your site starts below the historic memory, but the massive weight of your new skyscraper pushes the final stress past that historical threshold.
Crossing the yield boundary is critical. You cannot just average the recompression stiffness and the virgin stiffness together to save time.
You can't.
No, you must mathematically split the strain calculation into two distinct physical phases.
Okay.
First, you integrate the rigid recompression branch using M sub r all the way up to the exact point of the yield stress.
Right.
Then you stop the calculation,
Okay.
you switch your mathematical gears, and you integrate the much softer virgin compression branch from the yield stress up to your final structural load using the virgin M and J.
So in our suitcase analogy, crossing yield is starting out by just pressing on the clothes that are already in there.
Right.
But then you keep pushing because you're trying to shove a massive pair of ski boots into a bag that has never accommodated them before.
Yeah, that's exactly it.
Right? Suddenly you hit the structural limit of the fabric, the zipper strains, and the resistance totally changes. And the sources include a massive warning about this. They say using a single M value across both recompression and virgin compression is usually not defensible.
It isn't defensible because the stiffness before yield and after yield are drastically different.
Wow.
Treating them as a single line vastly underestimates how much the ground will sink once that microscopic structure breaks.
I see.
However, this highlights a major issue with physical laboratory testing.
Oh, really?
Yeah. When we drill down 100 feet and extract a tube of soil, the physical act of cutting it out of the ground disturbs it.
Oh, sure. You're mangling it.
Right. That sample disturbance can artificially smooth out the test data, blurring the sharp, sudden transition between the stiff recompression state and the soft virgin state.
Oh, no.
Yeah, it makes the soil's geological memory look fuzzy.
Which perfectly transitions us to the practical side of this. We have this beautiful theory of mud and math, but how do engineers actually extract these specific M and J parameters from a disturbed, fuzzy tube of dirt in a laboratory?
Well, the primary physical test is called an oedometer test.
Oedometer, okay.
We take a small puck of the soil sample and confine it inside a rigid metal ring.
Like a brass ring.
Yes, a brass ring. It prevents the soil from bulging out to the sides, forcing it into one-dimensional vertical settlement.
Right, it can only squish down.
Exactly. Then we apply physical weights to the sample in specific increments and use a dial gauge to measure exactly how many fractions of a millimeter it squishes over time.
Okay, I follow the mechanics of the test. You're squeezing a dirt puck and tracking the yield stress.
Mm-hmm.
But I have to admit, when the sources started talking about using a log linear fit to get the parameters from that data, I got completely lost.
It could be confusing.
How do you go from measuring millimeters on a dial to defining J and M?
It's all about translating a curve into a straight line to find its properties.
Okay.
The tangent modulus M sub t changes constantly on a normal graph. But if you calculate the instantaneous slope for every small weight increment and then plot those values on a graph where both the x and y axes are logarithmic scales,
Okay.
that changing curve magically straightens out into a line.
Oh, I see. So by changing the scale of the graph paper, you turn a complex curve into a simple slope.
Precisely. And once it's a straight line, the geometry gives you your answers.
Oh, wow.
The downward slope of that fitted line tells you the value of J.
Okay.
And where that line intercepts the vertical axis gives you the value of M.
That's brilliant.
You're literally reading the Janbu parameters off the geometric shape of the lab data.
That is so cool.
It is, but you must be meticulous. You can only fit that straight line within a single consistent branch.
Oh, right.
You either plot the recompression data or you plot the virgin data. You cannot cross the yield boundary on the graph.
For sure, you can't mix the two.
Exactly.
Well, this raises a fascinating point for the traditionalists out there. Because for decades, engineers have used a completely different framework for this, called the C sub C method, or the compression index.
That's very common.
And our sources dedicate a lot of time pointing out that for fine-grained clay soils, where we know that the Janbu J exponent equals 0, the Janbu model is actually mathematically identical to the older C sub C method.
They're essentially speaking the same mathematical language with different accents.
Really?
Yeah. Assuming you have a consistent definition of the initial void ratio of the soil, you can directly convert one to the other.
Okay.
The Janbu modulus number M is entirely a function of the void ratio and the traditional compression index.
So wait, if I'm an engineer working purely with soft marine clay,
Okay.
Janbu is just a more complicated way of doing the exact same C sub C math my grandfather did.
Basically, yes.
Then why did Janbu bother inventing a whole new framework if the old one works perfectly for clay?
Because a real construction site is never just a homogeneous block of soft marine clay. Real geology is messy and layered. Picture a site where you have 20 feet of soft clay, where J equals 0,
Okay.
sitting directly on top of 40 feet of medium-dense sand, where J equals 0.5.
Oh, I see where this is going.
The traditional C sub C method completely falls apart the moment you hit that sand layer. It cannot accurately model granular material.
Right.
The brilliance of Janbu is that it provides a universal, unified framework. It allows an engineer to model the entire complex layered soil profile cohesively using a single set of integrated mathematical logic.
That is huge because you don't want to switch software programs or mathematical theories halfway down a borehole.
No, you definitely don't.
You want one cohesive model.
Exactly.
Well, let's put that model to the test with a tangible example from the sources. We've talked about the theory. Let's look at the integration.
Okay, let's do it.
Yeah.
So the fundamental physical concept here is that total settlement is found by calculating the vertical strain for every tiny increment of pressure and adding them all up along the entire stress path.
Right, and the sources outline a scenario with a 5-meter thick layer of sand.
Okay, so J equals 0.5.
Exactly. And the starting effective stress from the weight of the dirt itself is 100 kilopascals. We build our structure on top, and the final effective stress down in that sand layer increases to 200 kilopascals.
Right.
So because it's sand, our J value is 0.5, and lab testing gives us an M value of 200.
Okay, good.
Now, I'll spare everyone the audio calculus of square roots and brackets, but when you run those inputs through the Janbu strain formula, you get a vertical strain of about 0.004.
Yes. And finding the physical settlement is as simple as multiplying that vertical strain by the layer thickness.
Okay, so 5 meters.
Exactly. 5 meters of sand multiplied by 0.004 strain gives a total settlement of roughly 0.021 meters.
Which is 21 millimeters.
Exactly.
We plug in the stresses, dial in the sand parameters, and the model tells us the sand layer will compress exactly 21 millimeters under the building.
It does. But I must add a massive caveat here.
Okay, what is it?
That 21 millimeter calculation is a highly simplified academic example.
Oh, right.
Because it assumes the pressure from the building remains totally uniform across the entire 5 meters of sand.
Which it doesn't.
No. In reality, pressure dissipates as it travels deeper into the earth. The top inch of that sand layer feels significantly more stressed than the bottom inch.
Right. The deeper you go, the more the load spreads out. You can't just treat 5 meters of dirt as one giant block.
A truly defensible calculation requires sublayering.
Sublayering.
Yeah, you have to stratify the ground into very thin slices.
Okay.
You compute how the load-induced stress decays with depth, select the correct recompression or virgin branch for every single individual slice, integrate the strain for each slice, and then sum them all up.
Wow. Still, 21 millimeters sounds incredibly precise.
It is.
But engineering is just as much about recognizing your blind spots as it is about running the numbers. So where does this beautiful Janbu model fall short? Let's talk about the boundaries of the theory.
Oh, this is perhaps the most vital takeaway for any practitioner.
Okay.
The absolute biggest limitation of the Janbu Tangent-Modulus method is that it only calculates the one-dimensional magnitude of primary compression.
Meaning?
It only answers one question. Vertically, how much will the ground sink?
Magnitude only.
Yes.
Which means it is entirely blind to time.
Completely blind. It does not calculate the consolidation rate, so how fast the pore water is physically squeezed out of the soil matrix.
So Janbu can tell you with great precision that your foundation will sink 21 millimeters, but it is mathematically incapable of telling you whether that 21 millimeters will happen over 3 weeks during construction or slowly over 30 years.
Exactly. Furthermore, it does not calculate secondary compression or creep.
Creep? That sounds ominous.
It is. Creep is the continuing long-term strain that happens after the primary water has already escaped.
Oh, wow.
It involves the highly complex, slow-motion rearrangement of the particles themselves, and it is a massive problem in highly organic soils, peats, or landfills.
So if I'm an engineer and I hand a client a Janbu magnitude number, slap a cover page on it, and call it a complete long-term settlement analysis,
Oh, please don't do that.
I am setting myself up for a massive lawsuit because I have completely ignored how long it takes and the slow creep that follows.
It would be a severe, potentially disastrous misrepresentation of the model's capabilities.
I need to know.
And there was another critical warning in the literature regarding advanced software.
Okay.
You should never take your Janbu M&J parameters
Right.
and blindly type them directly into a 3D finite element method, or FEM, software program.
Why not?
Because Janbu is strictly a one-dimensional mathematical framework.
Oh, right. It only looks at vertical squish.
Exactly. It inherently assumes the soil cannot bulge outward laterally. But a 3D model requires parameters like Poisson's ratio to calculate that lateral bulging.
Okay.
So if you plug 1D stiffness parameters into a 3D model without performing a constitutively consistent mathematical conversion,
Right.
the model will output pure garbage.
Garbage in, garbage out.
Exactly.
Well, to keep us grounded in reality, the sources actually provide 5 explicit checks to ensure a Janbu settlement profile is professionally defensible.
Yes, they do.
So if I want to make sure my building is safe, how do I check my work?
Okay, so the first check is fundamental: equation and units.
Right.
You must explicitly confirm the exponent convention your software is using. Like you said, is it looking for J, A, or N?
Ah, right, the beta trap.
Exactly.
Yeah.
And ensure your effective stress units perfectly match your reference stress units.
Okay, that's step 1.
The second check is stress history. You must clearly map the groundwater table, the initial effective stress, and the historic yield stress. But more importantly, you must explicitly document whether each individual sublayer calculation crosses that critical yield boundary.
Which is the trapdoor we talked about earlier.
Exactly.
Okay, so check 3 is parameter evidence. Like you said earlier, I can't just guess an M value from a textbook.
Right. You have to document the lab testing fits, the in situ cone penetration correlations, or clearly cite the sources if you're just using typical values for preliminary screening.
Got it. And check 4.
Check 4 requires robust numerical integration.
Which means slicing it up.
Yes. You must verify that you are slicing the ground into enough thin sublayers to capture the rapidly changing stresses, particularly at boundaries where the groundwater or soil properties suddenly shift.
Okay. And finally, check 5.
Validation. Don't operate in a vacuum.
Meaning compare your results to other models.
Exactly. Compare your sophisticated Janbu results with conventional C sub C estimates for the clay layers. Look at real-world settlement observations from adjacent buildings or run an entirely independent model. Sanity, check the math.
Sanity check the math. I love that.
Yeah. If an engineer rigorously follows those 5 checks, the Janbu method is incredibly powerful.
Yeah, it really sounds like it.
It forces a complete transparency regarding the relationship between soil stiffness, geological stress history, and numerical integration.
It's amazing. Soil just isn't a simple spring. We can't treat it like a steel beam.
No.
Its stiffness is a moving target, fundamentally dictated by a microscopic memory of its past.
Beautifully put.
And Janbu gives us the exact map, using that modulus number M and the stress exponent J, to track that moving target slice by slice deep into the earth.
Yes.
It basically demands that we respect the soil's memory. We can't calculate the future without understanding the geological past.
We really can't.
Which actually brings me back to our suitcase analogy.
Okay.
And a thought I really just can't shake.
The thought of the zipper breaking on the suitcase.
Exactly. Because we've spent this whole deep dive focused on the critical importance of that yield boundary. The tipping point where the dirt transitions from stiff, rigid recompression into soft, yielding, virgin compression.
Right.
And we've talked about effective stress as the weight of the dirt and the buildings pushing down.
Mm-hmm.
But effective stress is actually the total weight minus the pore water pressure pushing up.
Right. The internal buoyancy of the soil matrix.
Right. And right now, climate change is drastically altering groundwater levels on a global scale.
It is.
We are seeing severe, unprecedented droughts in some regions that are just draining aquifers, and then rising sea levels or extreme flooding, raising water tables in others. So the internal buoyancy of the soil beneath our cities is fundamentally shifting.
It's a huge issue.
So my question is this: how many existing, seemingly stable foundations out there are currently experiencing a silent shift in their effective stress paths?
Oh.
Right. How many structures are slowly, invisibly creeping closer and closer to that critical yield point, entirely because the groundwater is changing beneath them without anyone even knowing the suitcase is about to burst?
That is a mathematically terrifying reality.
Yeah.
Because the geological memory of the soil is fixed, but the environmental hydrology around it is changing faster than our infrastructure was designed to handle.
Right.
A shift in the water table changes the effective stress just as surely as adding another floor to a building.
Wow. Well, that is definitely something to keep you up at night the next time you look at a city skyline.
Yeah, absolutely.
Thanks for unpacking all this with me.